All right, 99% chance for a snow day tomorrow. So get your math fill in today. Okay. We are going to cover 8-6 day 2. We broke this into a couple days, maybe even 3 days. And today we're going to talk about the radical stuff. That's a lot of people think they're square roots, but you could have cube roots too, fourth roots, fifth roots. So we'll talk about those, and then we'll talk about how that relates to rational exponents. And a rational, like, I don't know if you think about, like, when you hear rational, you should hopefully think could be expressed as a fraction. So now we're talking about rational exponents is expanding exponents to be like to the 2/3 power or to the 1/2 power, stuff like that. Okay, so let's get right into it here. Here's a little definition of some terms. So the nth root of a real number can be written as a radical expression, the nth root of a, where n is the index. So the big thing to take away from this page is the index is talking about this. Okay, so whatever root it is, whether it's square root, cube root, fourth root, and then the radicand is the number or the expression that is inside the radical symbol. So down here it says, what is the index of this problem? The index is 5. Mr. Dahl, we're live here. What's going on? Mr. Dahl, they immediately start clapping for you. We're live on YouTube.
Well, I can't be interrupting then.
No, you can. It's more good. It's more good when you interrupt.
Didn't
Didn't I do this already?
Do
Let me see. I should have.
Are you right there?
Let's see here.
So you must have did it Friday?
Yeah, I think I did it Friday. But I don't see my signature on there. When?
Oh, here, do it on this page. Oh, if you did it, then you did it. A lot of people did it yesterday. Just those 2 pages.
Yeah, it should be on here. There I am.
Oh, got it. Sorry.
All right, yeah, I did it. Hey, good job. All right, back to work. That's what it was.
I'd rather have a bottle in front of me than a frontal about me.
Good one. Now I'm choking on my spit. Wow. I don't know if you picked that up at home. Hopefully not, but Mr. Dahl, he's a beauty. Radicand. Radicand is the number inside of there. Back to the boring stuff. Okay. All right, so a couple terms. The one I'll use more is index. That's the index of the root. 5 is the index of the root. So you'll hear me say that. Okay. Moving forward, let's do some practice. This is from Friday, so just simplifying some radicals that are higher than square roots. So fourth root. So here we go. So this is where we're going to try to simplify a fourth root radical expression. So I'm going to break this up into 2 parts. A part that has perfect fourth root stuff and a part that doesn't. And so if you look at the number out in front, 81, 81, hey, lo and behold, is a perfect fourth root. So the whole coefficient is a perfect fourth root. And guess what? X to the 12th is also a perfect fourth root because it's a multiple of 4. So that one, the whole doggone thing was a perfect fourth root. Isn't that neat? So all the radical stuff is going to go away here, and this is going to be 3x to the 3rd. Ka-chow. Yep, I just said that. Yep, this is review from Friday. So, except for maybe number 4 might be a little different. Number 2, break this up, couple perfect cubes. So perfect cube stuff, not perfect cube stuff. Perfect cube factors of 162 is going to be 81, is it? 81 and no, 81 is not a perfect cube. I'm looking at the wrong one. I think it's 27 and 6. So 27 is a perfect cube and 6 is not. And y to the 15th is a perfect cube there, so we're good there. Now the perfect cube stuff, perfect cube 27, that's 3. Y to the 15th is a perfect cube, that's y to the 5th. You take 15 divided by 3, you get y to the 5th. And then what's left in the radical is the cube root of 6. Ka-chow. Okay. Number 3, 24, that has a factor of 8. So again, perfect cube, not perfect cube. I'm going to go kind of fast here. 8 is a perfect cube, 3 is not. Y to the, now if I count down from 23, what's the next biggest number that's a perfect cube, or in other words, a multiple of 3? 21, good. So y to the 21st is a perfect cube because it's a multiple of 3. It's 3 times 7. And then what's left is y to the second over here. So perfect cube 8 is going to be 2, and y to the 21st is 21 divided by 3 is 7. And then what we have left in the cube root is 3y squared. How's that? How's that going for you? Is that all right? Is that making sense? Is that a Des Moines Buccaneers hockey sweatshirt? Wow, nice. Old Iowa girl. All right here. This one's tricky because this is a cube root and this is a square root, so you can't really multiply them together. But it's a happy little math book problem, just like Bob Ross would have liked. Cube root of 27y to the 18th, that's a perfect cube. That's 3y to the, class? 6th. Woo, good. Scared me for a minute there. And then 36y to the 18th, that's a perfect square. That's 6y to the 9th. Good, because that's a 2 right there, see? So if you're thinking perfect squares and it's a power, it's a variable to a power, you end up actually dividing. So now I can put those together and make 18y to the 15th with the ka-chow. Yay? Nay? Any questions? Feel free to jump in. Your eyebrows are lowered, so that means I think you're puzzled a little bit. What are you wondering about? Got it? 3 times 3 times 3? Yep. Okay, good. Anything else? All right, keep on moving. Now we'll talk about having these radicals in the denominator. Even in 2019, we're still not allowing radicals in the denominator, even though we have calculators. But this is old school, so we got to rationalize the denominator. It means we get rid of that radical, we multiply by itself. Now really we multiply by itself if it's a square, right? How do you get rid of a square root? Square it, right? You multiply by itself, you square it. So this one now is going to be 3 root 6 over 6. And then actually that reduces a little bit more. The 3 and the 6 cancel out, leaving root 6 over 2. Remember that? This is called rationalizing the denominator. This is root 15 over root 15. There's another way you could do it too. You could cancel, you could factor root 5 and root 3 and cancel root 5s, but it's not too big to deal with. So I'm just going to go this route. Root 75 over 15. Root 75 has a 25 in it, so it's a root 25, root 3. And that's going to be 5 root 3 over 15. So 5 root 3 over 15, and guess what's going to cancel out here? 5 and the 15, leaving a 3. Final answer is going to be root 3 over 3. Ka-chow with cloud. Yep. If it was 5 root 3 over 5, yeah, that would just be then just root 3. Yep, 1 root 3, which no one writes 1 times. Okay, now down here is a little bit more fun because now we have 1 over the cube root of 4. So listen, if you want a cube root to go away, you have to cube it. So now it's a little trickier. We have to multiply by root 4, cube root 4 times cube root 4, a grand total of 3 times. But it's 3 total. I kind of know what you're thinking. So if I go back up here to this one, okay, there's a 2 there, right? So I didn't multiply by root 6 twice. You know what I mean? I multiply by a total of 2 root 6s. So down here, if you want to get rid of a cube root, you got to multiply by the cube root 3 times. So cube root 4 times cube root 4 times cube root 4 is the same as the cube root of 64, which is 4. So the root goes away. The root part goes away because we made a perfect cube because we multiplied 4 by itself 3 times. That's how you make a perfect cube. 4 times 4 times 4. Yep, so it's like if you multiply by the cube root 3 times, the cube, all the root stuff goes away. You could have like 7th root. Yeah. Yep. The numerator stuff then will be the cube root of 16, but that has an 8 in it. So that's going to be cube root of 8 times cube root of 2 all over 4. Excuse me. That is 2 cube root 2 over 4. And then guess what happens here? 4 and 2 cancel out, leaving a 2. So that's going to be cube root 2 over 2. Legendary cube root 2 over 2. Okay. All right, moving on. Now we have fourth roots, cube roots of like whole fractions. So this isn't too big of a deal. We are going to break these up. Well, first see if anything simplifies in here. Does anything simplify? No, nothing simplifies, so forget about that. So now let's break it up into parts. Fourth root of x to the 8th over the fourth root of 3. Fourth root of x to the 8th, and the top is a perfect fourth root, so that's going to be x squared. And in the bottom, we have this crazy fourth root of 3 going on. So we got to multiply by how many more? 3. I could write out, the fourth root of 3 cubed, but I think that kind of tends to confuse you, so I'm just going to write it all out. And then there's all these little 4s in here. Wait, oh my gosh, what did you do? Sieve, 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 sieve. And then we got all these little 4s here, right? God dang it, I wanted that in green. Anyway. In order to make a perfect fourth root, you have to have 4 multiples of 3. Or 4 factors of 3. So 3 times 3 times 3 times 3 is going to be 81, which is a perfect fourth root, 3. So the fourth root of 3 times itself 4 times just cancels out and it just gets 3 over, and then the top we have x squared times the fourth root of 27. And there's no perfect factors of 27, so thankfully we don't have to do anything else with that. So we're good. Okay. Next one, we have 4, because it's, she asked why can't you simplify 27? Because there's no perfect fourth root factors of 27, right? Perfect fourth root factors they get pretty big pretty fast. It's 1, 2 times 2 times 2 is 16, and then 3 to the fourth is 81, so there's no perfect fourth root factors. Okay, next one here, let's break this up. We have the cube root of 4 n to the 9th over cube root 5. Cube root of 4, that doesn't do anything, but the n to the 9th part does. So we have n to the 3rd cube root of 4 all over cube root of 5. multiply cube root of 5 a total of 3 times to rationalize it. Why do you take the n out? Because so this is like perfect cube stuff, not perfect cube stuff, right? So the 4, no, there's no factor of 4 that's a perfect cube, but the n to the 9th is all perfect cube stuff, right? You can factor it apart, yep. So this is kind of crusty, but what we have over here is the cube root of 100. So we have n cubed is not, there's no radical on that. Then we have the cube root of 100 all over 5. And the cube root of 100, there's no factors of 100, so again, we're good on that. Hopefully. Okay, these are getting kind of crazy over here. So I'm going to, well, I guess number 7's not bad because the denominator is a perfect cube. So it ends up just being 3x, right? Because 27's a perfect cube and x cube's a perfect cube. So that becomes 3x. And then the top part just becomes, if I break that into like that, x and x, cube root like that, it becomes x squared and then the cube root of x left. And then we do get a little simplifying that x cancels out with that. So this is x cube root x all over 3. So I might as well just finish it up here. This one is a little bit of a different one too because you can simplify before you do anything inside the radical. So n squared cancels with n to the 22nd, leaving n to the 20th. And then it's a 5th root of n to the 20th, so that ends up being perfect. And in the bottom you get the 5th root of 8, which is just kind of an annoyingly big number to multiply by itself, or multiply by it 5 times. But, you know, that's how you'd go with that. So your numerator would be n to the 4th for now, and then your denominator is going to be rationalized eventually because you have the 5th root of 8. But, you know, I'm not going to do it, but you would have to end up rationalizing by 4 more roots, you know, which would end up just being crusty. And I don't want to do it right now because I think we get it. Okay. All right, moving on. Anything on that? All right, now we get into the rational exponent part. So exponents that are fractions. Here's the rule cut out from the book. I'll kind of highlight the rule just from scratch. You can look at that and read through that if you want. I'm going to go ahead and just say if we have the nth root of x to the m, by definition here, that's the same as x to the m over n power. You could also have it written like this, the nth root of x to the m like that. They're the same thing actually, and that's the same as x to the m over n power. Okay, so this is kind of defining what it means to be an exponent that's a fraction. So let's look at some kind of a continuum of some easy examples. Let's use 4. 4 to the first, 4 to the second, 4 to the third. 4 to the 0 is 1. First is 4. 4 squared is 16. 4 to the third is 64, right? What does it mean to be 4 to the 1/2? Because that's in between here. Well, by definition, right, 1/2 is going to be the denominator is the index of the root, so this is the square root of 4 to the first power. So the square root of 4 is 2. 2 to the first power is 2. So to the half power is the same as the square root. Yeah. You could take the power and then take the square root of it. It's the same. You know, you'll kind of see that. Let's look at the next one in between. Let's go 4 to the 3/2. What happens there? Well, 4 to the 3/2 means we go the square root of 4 cubed. I think it's a little easier to cube it after, so you don't get the big number. So the square root of 4 is 2, and 2 to the 3rd power is 8. 2 times 2 times 2. And you could, like what Natalie was saying, is you could say, you could go 4 to the 3rd, square root of 4 to the 3rd. What's 4 to the 3rd? 64, right? Square root of 64 is still 8. It's just harder to work with those bigger numbers, so I tend not to do that. Right? 4 to the 5/2, same concept. Square root of 4 is 2. 2 to the 5th is 32. So now we start filling in the meaning of what are all these exponents that are in between that are fractions. One thing we'll do is we'll rewrite from exponent form to radical form and radical form to exponent form. So here's an example of that. And the thing that I like to just keep it simple and remember is the denominator is the index of the root. Okay, so you write your root, you make sure that your denominator is your index, and then your other numerator, hello, that one wonky on me, whatever. So your numerator then is what you do, you square it, cube it, whatever. Here's some examples of that. 64 to the 1/3 power, write it in radical form. Okay, well, write a radical then. Make your denominator, that's the one on the bottom, the 3, the index of the root, and make your numerator all of that to the power of the numerator. And then your radicand is whatever the base is, in this case 64. Cube root of 64 is 4 to the 1st power, which is 4. I mean, how neat is that? Four to the 5/2, I think I just did this one. That's going to be, if I want to write it as a radical, put the square or the radical symbol. Index of the root is the denominator, 4, all that to the 5th power. Square root of 4 is 2. 2 to the 5th is 32. Excuse me, you don't have a cough button on this mic. Oh, there's the assignment. That's it. All right, good. So we did that in under 25 minutes. Okay. What was the number again? 24? All right, let's go here. Here we go.